Welcome to another explainer. Today, we're going to completely dismantle a massive misconception pop culture has been feeding us about how spaceships actually travel through the cosmos. Because if you've ever watched a sci-fi movie and just assumed that navigating the stars is basically like driving a car or flying an airplane, just point your ship in the right direction and step on the gas, well, you are in for a really fascinating surprise. So let's dive right into this. It's the most natural question in the world, right? When we want to get somewhere here on Earth, we look for the most direct route, a straight line. So why wouldn't spaceships just point their nose directly at a target planet, like Mars or Venus, fire up those thrusters, and fly straight there? It seems completely logical, but in the realm of orbital mechanics, trying to fly in a straight line isn't just difficult. Practically speaking, it's literally the worst possible way to travel. To really get why, we need to look at the huge gap between science fiction and science fact. In sci-fi, we're totally used to seeing ships with their engines burning nonstop, right? Just lighting up the dark void as they carve a perfectly straight path to whatever alien world they're heading to. But real spaceflight is completely different. The reality is all about engine shutoffs and curved coasting. In fact, real spacecraft spend the vast majority of their journey completely silent, with their engines totally turned off. You know the exact kind of artwork I'm talking about. The classic sci-fi covers showing a spaceship halfway between the Earth and the Moon, thrusters roaring, just flying as the crow flies. But that concept, and thousands of illustrations exactly like it, is fundamentally wrong. A spaceship's trajectory is almost never a straight line, and the engines absolutely do not burn for the whole trip. To fly like that, you'd need an impossible, mind-boggling amount of fuel. And this brings us to the real secret of space travel: momentum. Think about how vehicles work down here. If your car engine dies, friction with the road and air resistance slow you down until you stop. But space? Space is a vacuum. There is no air resistance, zero friction to slow you down. Because of that, a spaceship only really needs its engines to fire for a few minutes to hit its target speed. And once it hits that speed, it shuts the engines down entirely. The ship's momentum just carries it forward, potentially for millions of miles. So, real spacecraft coast silently through the void. Literally just minutes after launch, the fuel is spent or the engines are deliberately cut, and the crew, or, the robotic probe, just coasts. They let that initial violent push from the rocket do all the heavy lifting, riding that wave of momentum for months or even years. It's actually a beautifully serene reality compared to the fiery chaos we're used to seeing on screen. And it is absolutely crucial for saving the massive amounts of fuel required to leave Earth. Okay, but that brings up a really valid follow-up question. If we have all this momentum and there's no friction out there to stop us, why can't we just use that initial burst of speed to coast in a perfectly straight line directly to our destination? Why bother with curves? Well, space might be empty of air, but it is certainly not empty of influence. The invisible elephant in the room here is the sun's immense gravity. Our solar system isn't some flat, neutral playing field where you can just draw a straight line. The whole thing is entirely dominated by the sun's massive gravitational pull. Every single object in the solar system, including the Earth, which we are launching from, is already caught in that gravitational grip. We are constantly being pulled inward while moving incredibly fast sideways just to stay in orbit. So you really have to wrap your head around this staggering number. 30 kilometers per second. That is roughly the speed the Earth is moving sideways as it orbits the sun. When a spaceship launches from Earth, it already has that intense sideways momentum. To travel in a perfectly straight vertical line away from the sun towards another planet, a ship would have to burn an astronomical amount of fuel just to cancel out that 30 kilometers per second of sideways motion. Fighting the sun's gravity to force a rigid, straight path, it's a battle we simply cannot afford to fight with current rocket technology. To make this a bit more intuitive, think of a boat trying to cross a really fast-flowing river. The current is inevitably going to push that boat downstream, creating a diagonal path, right? Or think of skipping a stone across the sky. Earth's gravity instantly starts pulling it down into an arc. Out in space, it's the same deal. Spacecraft basically have to surrender to the powerful currents of celestial gravity. So, how do engineers actually navigate this crazy environment? It's essentially a highly efficient three-step dance. Step 1, burn fuel intensely but briefly to reach a very specific, highly calculated initial speed. Step 2, shut those engines off completely to conserve your resources. Step 3, coast. But remember, you're not just coasting blindly. You're coasting on a mathematically perfect curved trajectory dictated entirely by your momentum and the gravitational pull of the sun and planets. As a spaceship leaves a planet, the very act of escaping that gravity naturally creates a sweeping trajectory. You don't shoot straight up and away. As the planet's gravity weakens its hold on the ship, the path naturally bows outward. That initial arc is essentially the spaceship catching the solar system's gravitational currents. It perfectly sets the stage for the long, sweeping journey ahead. Which brings us to the strict geometry of real space flight. Let's summarize the actual rules of the road here. First off, paths are never straight. Never. Instead, spacecraft follow either elliptical paths, think of stretched out ovals, or parabolic arcs. By treating the spacecraft almost like a multi-million-dollar celestial billiard ball, engineers leverage the laws of physics to calculate these beautiful, sweeping arcs that rely entirely on momentum and gravity to get you to your destination, essentially for free. The mechanics of space dictate that the absolute most efficient path, the one that doesn't require a ship the size of a skyscraper just to hold all the fuel, is a curve. You launch, you arc outward, and you just let gravity gently bend your path through the void until it perfectly intersects with whatever target you're aiming for, whether that's Mars, Jupiter, or Pluto. But there's a massive catch to this whole curved coasting thing. Planets are moving targets. Mars is zooming along its own orbit right now. So space navigation isn't about aiming for where a planet is today. It's all about predicting exactly where that planet will be on its own orbit months or even years from now, and then timing your own curved trajectory to cross that exact point in space at the exact same moment. Honestly, it is the ultimate game of precision timing. All of this leads us to a really profound realization that beautifully sums up today's explainer. In the practical, physical reality of space travel, the shortest line between 2 points in space is not a straight line. I mean, geometrically, sure, but realistically, fighting gravity to force a straight path costs way too much fuel and energy. The smart way, the efficient way, really the only way we can currently travel between worlds, is to surrender to the curves of the cosmos. But hey, science never stands still, does it? There are some tantalizing hints out there about the future of spaceflight. Things like atomic propulsion, which could offer such immense, continuous power that we might no longer have to rely on coasting. We might actually be able to ignore the gravitational currents, stop treating spaceships like thrown stones, and finally just fly straight. Until then, though, we travel by the elegant, invisible curves of gravity. Thanks so much for joining me for this explainer. Keep questioning what you see and keep exploring.